Okay. Today we need to proceed in our discussion because up to now we have maybe said many epistemological, methodological, mathematical things, and we framed the activity of a scientist in a general picture. But in order to make clear what we want to do, we need to give you an example, a specific example of mathematical model invented for describing some physical phenomena, using the epistemological ideas and principles which we have discussed in general. I recently spent some time in Russia, and I discovered that in Soviet Union they were following exactly the same teaching strategy as in Napoli when I was a student, and the one which I'm using with you now. We start with the philosophical problem, we ask ourselves how to find the mathematical model for real phenomena. By the way, the course of epistemology in the Soviet school was lasting 250 hours before starting studying mathematics. And also when I was in Warsaw, and I've spoken with Professor Leciński in Warsaw, Tomek is a very good friend of mine, you will know him in a few days, he is visiting me. He was very proud to tell me, also in Poland I had many hours of epistemology. The method, the scientific method which has to be used in order to formulate mathematical models is very important. So, today, in order to proceed in the teaching strategy I want to follow for you, what we will do? We will decide that we want to model the phenomena of deformation of a beam. We will follow the strategy used by Euler and Lagrange for finding the simplest model for a deformable beam. We will apply the general epistemological principle which we have discussed, and we will solve some simple problems of deformation of loaded beams. You should know already the equations, you should know already the process. Maybe you have used different symbols, maybe you have used a different method for deducing the equations, but the equation itself and the theory you should already know. So it should be easier for you to follow my logical steps, because the technical details you should already know. Okay? I have studied carefully the original papers by Euler and the original contributions by Lagrange. So I can tell you that what I'm telling you, I can assure you that what I'm telling you is exactly what has been done the first time in the history of science for deducing these equations. Okay, so if somebody here wants to challenge a difficult problem and he wants to invent new equations, he must take into account what has been already done for inventing new equations. So I will teach you how Lagrange. It is not clear. Somebody writes that he was 17 years old. Somebody writes that he was 19 years old. Somebody said he was 21 years old. Lagrange solved the problem formulated by Euler. And the equation of the beam, of the equilibrium of a beam, were invented together by Euler, who was a well-established scientist, and Lagrange, who was a very young beginner. Okay? Lagrange was studying in a very good school in Turin, school organized by Jesuits. If you do not know who Jesuits are, go to Wikipedia and learn. Jesuits were the intellectuals of Roman Catholic Church. They were the scientists among the priests of Roman Catholic Church. For a long while, they represented the most advanced group of scientists in Europe. Okay, so Lagrange was studying in this school, and he didn't ask every 20 seconds why I need to study this. He believed his professors, and at the end he managed to solve a famous problem, being very young. Okay, as the problem, mathematically speaking, is rather complicated, I will present you a simplified form of it, just to give you an idea of the process. So I tell you immediately, then I will repeat. We are finding the Euler-Lagrange equations for a beam in the hypothesis of small deformations. So we will assume to have a beam which is deformed with a small deformation. Okay? Okay, now let us follow slowly the procedure which we described in general. We have this beam. This is the physical object. Okay? We want to know how this beam is in equilibrium under applied loads. Okay? So we need to characterize the set of configurations to be introduced in the mathematical model for describing the state of this beam. So the idea of Euler is the following. I know that the beam is made of a section, and this section is translated along a normal, and we are building a cylinder. In this case, in the case of this beam, you have that the section is a rectangular section, and this section is displaced along its normal to form the volume occupied by this beam. By the way, in this way, what we are doing, we are using some concepts of Euclidean geometry. Okay, so we imagine to know what is a volume built with a planar section which is translated along its direction for building its normal direction for building a volume. Now, every model must use some simplifying assumptions. We said that, for instance, if you have a planet moving around the sun, we may decide that the thickness, the the radius of the planet is negligible. While you study the motion of planets, you say the planet is traveling millions of kilometers. The radius of the Earth is of the order of magnitude of several thousand kilometers, so the radius is small compared with the space which is traveled. So we conjecture that the thickness of the radius of the Earth is negligible. Euler says, I have a beam which is very long and the section is very small compared with the length. So I can assume that each section remains flat under deformation, and I can assume that each section remains orthogonal to the curve of the barycenters of the sections also after deformation. Is this conjecture always true? No. We are assuming this conjecture simply in order to develop a model which is valid in some situations. We will discuss when we can apply this model and when this model cannot be applied. So the idea of Euler is, instead of describing the complex geometry of my beam, I introduce a simplified geometry. Okay, a curve. The shape of the beam is described by a curve. And I conjecture that my mathematical model is detailed enough to describe many phenomena in which I am interested. Okay? At the beginning of his analysis, Euler was not sure. We know that this analysis is very useful, so we are teaching it to you. But you must understand that at the very beginning of the analysis by Euler, he was not sure that he was going to produce a useful mathematical model. To make this point clear, I tell you that Galileo Galilei, I hope that you heard this name, tried to study the deformation of a beam and failed. The conjectures by Galileo Galilei were wrong. So, it is not true that the first scientist who tried to find a model for a beam was immediately successful. And Galileo was not stupid, as probably you know. Okay. So, I have a physical object. Then I start considering its volume, the part of space occupied by this physical object. Then, for each section of this cylinder, I find the barycenter, and then I consider the curve constituted by all these barycenters. So we are proceeding in what is the so-called mathematical abstraction process. I have a physical object, I invent some mathematical entities in order to model some particular properties of the physical object which I have in my hands. Then I must distinguish between the reference configuration, which is the configuration where no external applied forces, this is a possible choice, we call it natural or not loaded reference configuration. And the reference configuration is characterized, for instance, by a straight line. This is true for this beam, but if you have an arch, the reference configuration is not a straight line, but a curve. A curve which is not straight. Okay? Okay, for simplicity, the theory can be developed for beams whose shape in the reference configuration is not a straight line. But for simplicity, we assume to have a straight line. Then we introduce an abscissa, capital S, which labels each section in the reference configuration. So this label is the label which characterizes each section of the beam. Okay? Then we must describe the change of shape. You have one shape, then you apply some load, this beam changes its shape. So in general, you must invent the set of possible configurations of, if you prefer, the possible set of shapes which this beam can reach. Okay? Now we follow Euler and we introduce the placement K of capital S. So, given S, K of capital S is the position where the barycenter of the section labeled with S occupies in the new shape. So the actual shape of your beam is the image of the interval 0, L under the function K of S. Now let us stop a little bit. Lagrange, Euler, when they introduced the concept of change of shape or configuration, they did not know a lot of mathematical analysis for a simple reason. This mathematical analysis was not invented yet. They invented it. So the concept of function has been developed, among the others, by Euler and Lagrange. This is a typical example of mathematical theory which has been developed in order to describe physical phenomena. So it is very useful for beginners, because when you study mathematical analysis, you spend all your life asking yourself, why should I study this? Is it useful? Many develop a theory that everything is a plot. Professors, in order to get their salary, invented a useless theory which is used for treating in a bad way students. Unfortunately, this is an a posteriori justification. You have the initial shape of a beam. The beam changes its shape. You need to tell to your mathematical model which section in the reference configuration is placed where. And you cannot use words for this. you need to use mathematical formulas. So if you have a reference system of reference with an origin and 3 unit orthogonal vectors, you can describe the position of your the barycenter of your section with respect to this Cartesian reference coordinate system. Key of S is key1, key2, key3, 3 functions of real variables telling you the position in the actual configuration of your beam. So this is very important in order to produce mathematical description of the shape of your beam. Okay? Now, do you want that your beam can be cut in the transformation from reference configuration to the actual configuration? Of course, there are beams which are broken. But Euler knew that he cannot produce immediately the most general theory of beam. A theory which includes inside elastic deformation, plastic deformation, and rupture. So he decided to limit the range of applicability of his model. So not only he assumed that every section remains orthogonal to every shape, so that if you have the reference configuration or if you have the actual configuration, if you know the tangent to the curve, you know the orientation of the section. I'm running. Somebody could tell me, you are assuming to know which is the tangent direction of the curve in every configuration. So you are making a lot of assumptions. Not only you are assuming that K of S is continuous, because it is not broken, but also you are assuming that in every point you have a tangent direction to the curve. So you are assuming that dk over ds is well defined. So you are assuming that your curve is C1 is a continuous function having a continuous derivative. So you understand that while assuming limitative hypothesis about the admissible deformation of your beam, you are building your space of configuration. Your space of configuration is a set of mathematical objects verifying some hypothesis. More assumptions you are assuming, more restricted is the range of applicability of your theory. So, for instance, if you have a stick and then you violently apply forces to it and it assumes this shape, so you have one point where your stick is not anymore represented by a shape which is one time differentiable, the theory of Euler is not applicable. And the deformation process from here to there is more complicated than the one proposed by Euler. Now, you understand the true reason for which you find difficulties in learning mathematical models for real objects. you need to know what it means a continuous function and what it means a differentiable function. Now, in the tradition established by École Polytechnique in Paris, you know, France is a place where the democracy of science has been invented in modern times. The French Revolution established the principle that everybody must be allowed to become a scientist. So they invented the Grande École, big schools, where everybody could enter if he's clever enough and where he can study high advanced science. In École Polytechnique, they established the principle that everybody, for becoming an engineer or everybody for becoming an architect, must know the definition of continuous function and differentiable function. Why? Because the theory of beam is fundamental in engineering, and you cannot understand the theory of beam if you do not know what it means that a function is continuous and a function is differentiable. Okay? So, mathematically speaking, the space of configuration is made with C1 functions defined in the interval 0L. Okay? And this is the mathematical model of all possible shapes of your beam. Okay? Now, if you have a beam which is deformed in space, key of S has 3 components, because in Cartesian coordinates every position requires 3 components. Now, for having our life simpler, we assume that the beam is undergoing planar deformations. So you have E1, E2, E3 is the vector coming outside the plane, and we assume that 2 coordinates are enough. So this displacement, so you assume that the generic section is placed in the point SE1, okay, and you assume that the section which is in the reference configuration placed in SE1 position goes in the position SE1 plus U of S E2 plus W of S E1. So you have an horizontal displacement, axial displacement, WS E1, and a transverse displacement, US of E2. Okay, so you assume that your beam becomes planar. This for making calculations simpler. Actually, we will do it even more and more simple. We assume that WS is 0. So you have only transverse displacement. So this beam is subject to a deformation which is produced by purely transverse displacements. Okay? So all these limitation properties, all these assumptions need to be said explicitly to you. Why? Because you cannot apply the theory which I'm developing in situations where one of these assumptions is not verified. So you need to know exactly all assumptions which are accepted, because if you know the assumptions, then you can apply the model knowing what you are doing. Now, what is very interesting is that this theory, which has been developed for studying the deformation of a piece of wood loaded and clamped somewhere, somehow, has been very successfully applied in many situations. You can apply this for describing the deformation of a bridge. You can use this model for describing the deformation of twin towers. You can apply it for describing the deformation of a beam made of reinforced concrete. Please consider this situation. All these things were built after that the model had been invented. So the model was invented, and then engineers looked for the situations where this model could be applied, could be used. And they built many things using this model. Okay? So let's proceed in our construction. So we consider the actual configuration, which is obtained with a function u of s. Now, I'm sure that you have studied, you know what is the graph of a function. So the graph of the function u of s gives you the actual shape of your beam. Okay? Now, I'm sure that you know what is a tangent curve to the graph, the tangent straight line to the curve which is the graph of a function. U prime of s, the derivative of this function, is the tangent of this angle. Okay? So, tangent of phi is equal to u prime of s. So, to say that your curve has a tangent everywhere is equivalent to say that the function u has the derivative in every point s. We cannot talk about the tangent of a curve without being allowed to talk about the derivative of a function. But I told you that we want to limit ourselves to study the case of beams which are deformed, which are in a regime of small deformations. Small displacements, small deformations. I hope you remember that the tangent is sine over cosine. And I hope that you know that cosine for a very small angle is nearly 1, and sine of a very small angle is nearly phi. So in the regime of a small deformation, u prime is nearly equal to phi. Okay? Euler and Lagrange were not assuming this. They were assuming they studied beam in large deformations. But I don't want to burden our discussion today with technical details. I want to end my discussion showing you how the principle of minimum of energy is very powerful for finding the equilibrium shapes of a beam. So I try to make the technical difficulties as small as possible. Okay? So let us assume that this angle is nearly equal to u prime. Okay? Now consider the section of the beam here and the section of the beam here. Our assumption is that it is always orthogonal. Okay? Now, which is the angle between the reference orientation of the beam, of the section of the beam, and the actual orientation of the section of the beam? This difference is exactly phi. Why? Because this is orthogonal to this straight line, and this is orthogonal to the tangent straight line. You remember there is a theorem of Euclidean geometry. Two angles are equal when each side of the angle is orthogonal to the side of the other angle. Okay? So this phi is exactly the change of orientation of the section of the beam, which we assume to remain orthogonal to the curve of barycenters. Okay? Why this observation is very important? There is another scientist who played a role in this theory. He was Bernoulli. Actually, there is a family of mathematicians whose name was Bernoulli. Okay. If I remember well, the Daniel Bernoulli was the mathematician who sent letters to Euler discussing about this. What is bending? What is the bending of a beam? The bending of a beam is the variation of orientation of sections when moving from one section to the close one. So you have phi of S plus ds, a small variation of S, minus phi of S divided ds. This is the rate of variation of angle phi when moving from the section S to the section S plus ds, where ds is a small variation of S. Okay? You should be more or less familiar with this. Okay? This is the derivative phi prime, merely the derivative phi prime, when ds is sufficiently small. Now, this was a big debate between Bernoulli and Euler. I have one beam which is straight. Then I deform it. Which is the mathematical object which describes the bending or the variation of bending between the reference and the actual configuration? The proposal of Bernoulli and Euler was phi prime is the variation of bending. What you have to understand is that, mathematically speaking, if phi, as you can call it, is equal to u prime, phi prime is equal to u second. So, I could tell you I am interested in u second without explaining you why. It is very difficult to explain you why. I'm trying to do it. The idea of Euler and Bernoulli is the following. I need energy for bending a beam. If I find a way for representing mathematically the bending will appear in my expression for energy. So I must invent what is called a measure of deformation. And the fundamental idea is the measure of deformation is related to phi, is given by phi prime. Because of the assumption of small deformation, phi is equal to u prime, so my measure of deformation is u second. By the way, if you have studied in every course of calculus, they are teaching you that u second is so-called concavity of the graph of a function, and concavity is a measure of lack of being straight. Straight lines have u second equal to 0, and if you have u second different from 0, the curve is not straight. Bigger is u second, and more it is not straight, roughly speaking. Okay, Euler invented this reasoning. I have this orientation. I have this orientation. I calculate the limit of the variation of this orientation divided the increment of the independent variable. I get phi prime, and phi prime is the bending. With the assumption of small deformation, phi is equal to u prime, so I get that bending is given by u second. So, bigger is u second, more the beam is bent. Okay? So now we are ready. We have concluded the kinematical description, the description of deformation. So we know, mathematically speaking, what it means that my beam has changed its shape. Okay, you may believe that this is not practical, it's not engineering. Many students came to me to say that all this is useless mathematics. I heard that some among you likes abacus or SAP or I don't know which software. Go and look how your software is studying beams. Euler's theory. They introduce the change of shape, they introduce deformation related to the change of shape, and this is what they have, what they call the kinematical description of the system. Then they need to introduce deformation energy. So this is what we do now. This is the shape of my beam. And my hypothesis is the following. The deformation energy of the segment, I don't know how they call it in Iran. I can tell you how they call it in Italy, in Germany, in France, in the United States. They call it infinitesimal element of beam. I'm sure they are calling it also in Iran like this. So I take all infinitesimal elements of this beam and I ask myself, which is the deformation energy of each infinitesimal element of beam? I postulate this expression for the energy. It is like a spring. It is a bending spring. You have a coefficient which is called bending stiffness Km divided 2 times u second square. This is very similar to the energy of a spring which is elongated. Hooke law for a spring is this one, where x is its variation of length. We say that each infinitesimal element of beam is storing an energy which is given by Km over 2 u second square. Okay, of course this is the energy per unit line. So in order to get the total deformation energy, I must calculate the integral between 0 and L over the S of this quantity. Okay, so this is the Euler-Bernoulli deformation energy. Okay, let us stop a little bit. Somebody tells you that this is given by experience. I don't know what it means. This is another conjecture. This is a conjecture like the one which we have accepted for the kinematics of the beam. We have assumed it is orthogonal, the section remains orthogonal to the curve of barycenters, and all the assumptions which we have done, including that u second can be calculated. Okay, we are developing a model with a series of conjectures. Okay, then let us try to solve the Galileo problem. You have a beam which is clamped in the section which we have labeled with 0. And we have a force F which is applied in the section having label capital L. Okay? So we are facing Galileo problem, which is the equilibrium shape of a beam which is loaded. Okay, as I am not a civil engineering, I will tell you the story. I will apply the force F in this way. You know, a colleague of mine many years ago said that the proof that I'm not a civil engineer is that I applied a force which is positive when it is going up. Because true civil engineers have positive force going down. I mean, this is a kind of mental disorder. I will go back to this point later. Okay. So now we have a very serious problem. How can I find the equilibrium shapes for this beam? I go to my epistemology. I know how to describe the configurations. I need to write an expression for total energy, and when I have the expression for total energy, I must find the minimum of the total energy, because every stable configuration shape is, equilibrium shape, is the minimum of the total energy. Okay. Euler is postulating for me this form for deformation energy. Is this everything? No, because we have the potential energy related to the dead load F, which is applied there. Okay? So if I have a displacement U in that direction, so if I have a displacement in the same direction as F, potential energy is decreasing, because I'm falling along F. So the potential energy related to F is minus integral between 0 and L of F of U. Sorry, there is no integral of U of L. I have only one force concentrated here. I will write later if I have a distributed force, but I want to make it easier. Okay? So you understand now why some true engineers want to have that the force is positive in this direction and displacement is positive in the other direction, because in this way the minus here is not needed. You place it here plus. This is a way for hiding difficulties, and it is a proof of a kind of mental disorder. Why the force is positive in one direction and the displacement is positive in the other direction? To suffer. Yeah, you want to suffer without, just for avoiding a minus sign. This is not the only reason for which this minus sign should be avoided. And I explain you why. Now, the total energy is this one. Okay? Now, the equilibrium is obtained when this total energy has a minimum. Okay? So what it happens? If the beam folds following F, so if the beam is doing this way, U of L is big, F is my applied force, this becomes very negative. So total energy decreases its value. Okay? equilibrium is minimum of energy. So this must become negative. However, if this becomes very negative, U second becomes very large. And so this becomes positive. What is equilibrium? Equilibrium is the maximum UL with the minimum U second. It is the interplay, falling, deforming. The equilibrium is obtained when the deformation is the minimum possible with the maximum possible of displacement UL. Okay? Of course, these are words. We must transform these words into formulas. Right? Okay, so I propose you to write a little, somehow more general energy, because we assume to have a force per unit line Bs. So we have, as I wrote before, minus integral between 0 and L of Bs us ds. You have a distributed dead load applied along this beam, minus eventually this F of applied in L U of L, and we stop for a little rest, but before stopping we remark the following thing. Here Euler stopped. After having formulated this minimum problem, which is the minimum problem, find the function us 2 times differentiable such that total energy is minimum. This function is the shape of equilibrium of your beam. Euler managed to formulate this problem, but he did not manage to solve it. Lagrange gave him the method for solving it. Okay? Why I'm stopping here? Because up to now I did the work of a physicist. The work of a physicist is to understand the phenomena, to understand the physical problem, to formulate the mathematical model for describing this phenomenon and this physical system. Then I go to a mathematician and I tell him, find the function us which makes minimum this energy. Now on, us is a function, b is another given function, f is another quantity. This is not anymore a beam. This is a mathematical problem. And we must solve it without knowing the physical situation from which this mathematical problem was motivated. The motivation of this mathematical problem becomes irrelevant. Why? Because it could be that U means another thing. Now, Our problem is the following: to find a function such that this quantity is minimum, given Bs and F and Km. Okay, so now on we forget all physics and we go to mathematics.